Let me first thank you very much for inviting me to this meeting. And I think we have done a terrific thing in the Modelica community, which I will mention here in my talk. So this is my outline. There will be a brief introduction. I will talk about computing. I will tell you how Modelica emerged, and then I talk about some challenges, and then I do a bit of a summary. And I do it from a control perspective. And here's my vision of the world. So naturally control is in the middle, and we are forced between the real world that's sitting up here. So here we have the real world, and then we have mathematics that are our tools, and then we have two help sciences, computing and communication. Another way to view it is this slide, which is coming from the National Academy of Engineering in the US. And they say that there will be growth in the areas of simulation and modeling around the creation of new engineering structures. Computer-based and design-built engineering will become the norm for most product designs, accelerating the creation of complex structures for which multiple subsystems combine. So this was a study they made when they were discussing what engineering was going to look the year 2020. That means next year. From a control point of view, I call it the magic of feedback. Because feedback can do amazing things. We can reduce variations to disturbances. You know, when the car hits a hill, goes upwards, it goes slower, so then the control system fixes that. We can reduce the effect of disturbances. We can actually make good systems out of bad components. We can also stabilize and shape behavior. We can make a system follow command signals. So these are some amazingly good qualities, and that's why control is so widespread. Of course, there are drawbacks. Number one, whenever you close a feedback loop, you may run into instability. And that's why stability theory has been such an important part. The other thing is whenever you're feeding a measured signal into a system, you're feeding in measurement noise. So you have to make sure that that is not so much. And here I have a little support by one of my favorite authors, Arthur C. Clarke. You know, he writes science fiction. He says that any sufficiently advanced technology is indistinguishable from magic. And therefore, I think it's justified to call it the magic of feedback. Now, when we do control, models is used in all the steps. It's used when we are simulating, when we're doing control design, when we do validation, when we deliver performance guarantees, when we implement, when we do fault detection, we do diagnostic to do reconfiguration. So modeling is a real essential part of our lives. Unfortunately, the real world is complex. We have many different physical domains. As a control engineer, you may work in something with chemicals, you may work in something with mechanical, you will work in something with electrical. So we have a very large physical domain to operate in. And also, there are often large physical dimensions. There can also be very small physical dimensions. We go all the range from nano to giga in control. And then systems have a pretty complex behavior. And it's getting more and more complex as you try to save things, as you do recirculation, etc. It's a big difference when you're designing a process from scratch together with a control system, and when you're presented with a system, and then you say, please control this. So there's a tremendous advantage to do concurrent design. And of course, we have mixtures between continuous and discrete systems. So here's a typical control system architecture. Here is the system we are trying to control. And here's what the controller can look like. There's something here called feed-forward generator. So here's a command you give in, and then you do two things. You put in signals here that will make the process to move in the right directions. And also in here, you tell how all the important variables should behave. And if everything works out all right, there were no disturbances, it's only this signal does all the job. But if there are uncertainties, you made a small mistake, then you have here something I call the Kalman filter or observer, and that is receiving all inputs we send into the system and all outputs, and then it figures out based on mathematical models what are the important variables that we cannot measure directly, and we get filtered versions of signal we can measure. So then we get here all the important variables, and then this is also delivered by the feed-forward. And if this agree, this signal will be 0, and then we do nothing. But there are some deviations, then this feedback signal will step in and do the job for us. Now, if you look at this, you see there are models everywhere. In here, there are models. And we also have to generate this one, we have to have inverse models. In here, when we do the filter, in here is a dynamical model of the system and its environment. And also when we compute the design here, there are models inherently when we're computing design. So models is really a part of our lives. The way we deal with this is that we use computing. Here's a slide that tells a little bit about the history of computing. Vannevar Bush was a professor of engineering at MIT working on power systems. And in 1927, he said that engineering can progress no faster than the mathematical analysis on which it's based. Formal mathematics is frequently inadequate for numerical problems. A mechanical solution offers the most promise. And then he built the mechanical differential analyzer. A mechanical monster that you program with wrenches that could solve about 6 differential equations. I had the pleasure of working for IBM for 5 years. And I was part of the time in the math department in Yorktown Heights. And we had a great guy called Hermann Goldstein. He actually built one of the first computers together with John von Neumann when he was in the army. At one of the staff meetings, he said the following: when things change by 2 orders of magnitude, it is revolution, not evolution. So when you can do things 100 times better, that's something drastic happening. You compare this with Gordon Moore's, which is no longer valid, you find that in computers you have a revolution every 10 years. So roughly every 10 years, computers became 100 times faster. And this happened, for about 50 years. This has not translated into engineering productivity. We have not become 100 times more efficient in 10 years. And 10 to the 4 times more efficient in 20 years. So, and the reason for that is that algorithms, software have not delivered corresponding advances. You can see this as a bad thing. You can also see it as an opportunity. And I think Modelic is one thing that could help this opportunity. Then we are going to talk about modeling. And here is one modeling paradigm. It's taken from a nice German book called Kleines Handbuch der Regelungstechnik. It's about that thick. And he has this nice picture. He said, we don't care about what's inside the boxes in here. We just care, here's a signal coming in, here's a signal coming out. And then you draw these little squares, you get a block diagram. So this is the traditional block diagram modeling, which is tremendously useful. To describe the Book's ordinary differential equation, there are causal inputs and outputs, and it's a very useful abstraction. It's the key for analog computing. It's essential for control, but not for real physical modeling. I thought I had a slide for that. And the reason for the physical modeling is that if you take 2 systems and connect 2 capacitors and connect them, you get a spark, and then the capacitors have the same voltage. So then 2 states disappear. The same if you have rotating mechanics, you have 4 states, angular, velocity, and position. You connect the 2 together, you get scratches, and then they rotate with the same. So states disappear when you connect physical systems. The other thing is that you can't combine systems one after the other when you do it. So analog computing was based on that. You were solving differential equation, and Bush did it first with mechanical, then we got electrical computing, and you create a feedback loop. So here is a nonlinear function and integrator, and then you get a feedback loop and you solve it. And if you close a loop without having an integrator, you get an algebraic loop. So the analog computer started to tweak, started to whistle. And there was another thing. When you have the physical devices, they operated typically on plus minus 100 volts or plus minus 300 volts. When they got out of range, you get an alarm signal, so you know that something is wrong with your model. And there have been many versions of this, and I would say that Simulink is the ultimate block diagram tool. It mimics analog computing. Each block is a state, and you have MATLAB and state flow. You have granularity and structuring by essentially doing graphical thing. On the other hand, you need to do much manual or manipulation to go from physics to blocks, and also syntax and semantics are not available. And here comes the reason why this is not good. So here you have the story about the 2 capacitors. And then if you model a tank like this with a block, and then you connect 2 tanks, it doesn't map like this, because the behavior of this tank depends very much on the pressure here, which depends on what this tank is. So if you model this as a block, this is not 2 blocks in the world. So number 1, that's why I'm saying that block diagrams are not suitable for serious physical modeling. Or in other words, this paradigm came from analog computing. And now when you get digital computers, you should not necessarily stick to an old paradigm when you get a new thing. So I'll tell you a little bit how Modelic emerged. And first I give you a slide. Here are some modeling tools. And the civil engineers were first out. around 1956, they started to do structural dynamics. Chemical engineers came a little bit later, 8 years later, at Imperial College. I'm very glad that Pantelidis is here, because he was part of that group when they did the first simulators for chemical engineering. Electronics was pretty early, about the same time, with IBM and also with Berkeley. And then you get more structural dynamics, you get more electronics. Building simulators came out around 1975. And Daimola came out in 78. And this was the first general purpose modeling language. They were cutting across several different disciplines. I'll talk more about this. And then later on, you see, there were more things coming up. And in 1996, we got Modelica. So then, since we were part of this, I have to tell you about Lund Institute of Technology in the 70s. I became professor there in 1965, after spending 5 years at IBM. So I came to a new department in an old university, and we started a research program in control. We did optimization, computer control, system identification, adaptive control. And I also said, that was something I learned at IBM, we should at all times have an honest application in the group. And what do I mean by an honest application? Well, it's something that comes from outside, from industry. It's something where you have deadlines and something where you have to deliver. And that gives a very healthy atmosphere in a research group. You have, the people are flying up with the ideas, and then you have some people who are really trying to solve a real, genuine problem with outside interest. So we very quickly figured out that to solve control problems, we had to do a lot of modeling. And also, in order to work efficiently with industry, we needed to develop tools. So we developed a string of tools. We had toolboxes for, this was an interactive box for doing control system design, for doing system identification. This later grew, one of our PhDs was Lennart Ljung. This later grew into the MATLAB system identification toolbox. We had modern transformation things. They were all written in Fortran, and they were distributed to industry. One of the leading guys was Johan Wieslander, and a nonlinear simulator was missing. And I had worked in the control group also at IBM in San Jose, where they developed one of the first digital emulators of analog computing. So we had this early design chain, and there were quite a lot of users. It was a real breakthrough when General Electric required, they took over all our software, distributed them internally within General Electric. Gave us also very useful feedback of this. There was one thing that was missing, and that was a nonlinear simulator. So I got a nice, smart master student, Hilding Elmqvist. And he wrote a nice digital emulator of an analog computer. And there are two things. Number one, with the programs at that time, if you change a parameter, you had to recompile. And that took a lot of time in these days. So number one, we wanted to change parameters without having to do recompilation. Secondly, we wanted to have it interactive. And Hilding, he also wanted to do real language. He wanted to have a real language definition. So he defined a very nice little language. You had a continuous system. You had inputs, output, state. You write down equations. You could also do a discrete system. We could simulate computer control. So one important thing is here, TSAMP. That is the next time instant when this block is going to come into operation. Very nicely done. And then you have something to connect the things. And here you see a young picture of Hilding in front of Johan Wieslander. And we had one thing I was insisting on. I tried very hard to get our own computer in the department. And we had a fantastic rector at the time when I joined there. A great academic leader. He was the rector of KTH. So I had lots of money, and they had lots of stuff to buy. I didn't want to have anything. So I went up to him. I would like to buy a computer. And they said, that might be troublesome, he said. But let me think about this. So then come back in a week, he said, in the current rules, we can't do it. Can't you call it something else? So we called it a process controllers. And that's how we got our first computer. So it was a PDP-15, where it's a very useful machine. We also did another thing. We worked very closely with a local power company, Sydkraft. And they had a power station in Malmö, not far from here. And they have been discussing to closing this down in Sweden right now, but I read in the newspaper they're going to restart it again because we have lack of power in. So it's a 160 megawatt power station. And we did lots of experiments of this. We were putting in perturbation signals and all the variables we were modeling. So we had some very good models of this. And here is one model, the final model of this, written by a guy named Sture Lindahl. It's about 173 pages. A very detailed model of this, which was very useful. So that was something we had as a model to do it. We tried several things. One of the first things we tried to do model and abstraction was bond graphs, invented by Hank Painter. And then we discovered that bond graphs are nice if you have only one essential balance, for example, an energy balance. But if you are doing thermofluid systems where you have to take care of mass balances and momentum balances, you end up with a horrible mess. You had 3 sheets for each balance, and then you have threads going between them. So we decided that it was useless for series physical modeling. Perfect if you only capture everything with an energy balance. And I had a nice verification of this when I was on sabbatical in Texas, because in Texas they had 3 of Painter students there. So I challenged them with our model and said, could you describe this in bond graphs? And they admitted, bond graphs is not suitable for this. Another thing was electronics, where you have multi-port systems. And Berkeley had a simulator for that around 1970, which has many nice things. And the nice thing is that they were working with equations. And also, this has become an IEEE milestone for 2011. So IEEE decided that this simulation program was so important for the electronics industry, they made it a milestone. So then what is physical modeling then? Well, you have to cover wide physical domains. We have to divide system into subsystem and define interfaces. We use object orientation for structuring, and then we write down mass, momentum, and energy balance for subsystems. We describe systems by differential algebraic, not ODEs. We have constitutive equation and database for libraries. We have libraries for reuse. We do a lot of symbolic computation. And I'm so glad that I will meet Pantelidis today, because they were the group who really pioneered symbolic computations. So the question was that Hilding had done a very nice master thesis. What should they do? There were lots of demands, to make a drawback of saying we only had real variables. So many people want to have vectors and stuff like this. There were lots of demands for this. So Hilding and I were sitting and talking and said, well, we could do this, but, the transpiration factor is too high. The ratio between transpiration and inspiration is too high. So what should we do? Well, we knew that modeling was a key issue for us in control. So we ended up with saying that, why don't you start to look seriously at the problem modeling physical systems? And that was the part of Hilding's dissertations. And he had the inspiration from electrical systems. Oh, I'm sorry. He had the inspiration from electrical systems, from chemical engineering, from multibody. And so he wrote the first was called Daimola. It was based on object orientation. He used a Norwegian program called Simula. That was at the time the only object-oriented program that was available. And I said, Hilding, I won't pass your thesis unless you can compile the Boiler model. So, he could play around and do many things, but he had to compile the Boiler model. And of course, he did this, and I think he compressed this into about 11 pages or 12. And the power system company was so interested. This is a very interesting way of documenting a fairly complicated system. So we got a lot of credit. Now here's Hilding's thesis. I have a copy with me in case anybody here would like to take a look at it. So it was a great idea, but it was premature due to lack of software. Simula was not widely used industrially. Later on, they got the Turing Prize in computer science for doing Simula. But at the time, it was not used in industry. So we said that this is too early. It's a good idea, but it's premature. Well, we had this program, Computer-Aided Control Engineering. So in around 1990, we started a new project called Object-Oriented Modeling and Simulation. And Sven-Erik Mattsson was one of the key drivers for, and Dag Bryck, who is present here, was a key actor in this. So we had a group in the department of about 5-6 people who were doing this. We did experimentation in Lisp, which had very nice object orientation. And then we had C++. And they developed a language called OML, Object-Oriented Modeling Language, and Object-Oriented Simulation. And there was a lot of symbolic manipulations, index reduction. And Sven-Erik, he did a thesis on control of wind turbines later on. I had to retire at the turn of the century. And when I approached my retirement, it was unclear if my successor was going to continue this research activity. It was quite a major part. At the same time, Hilding had left the department. He wanted to do computer science, so he went to Stanford for a while. And then he came back to the department. He did a very nice distributed control system. And then he went to industry to implement the distributed control system there. And then he decided he wanted to do something serious with his program Timula. So he came to Lund and he started the company Dynasim. And he started to build up this. And this was very fortunate because he wanted to have good people who knew about this. And I had good people who were questionable what their status would be when I retired. So Hilding took over to Dynasim a lot of these people. Dag Brick, Sven-Erik Mattsson, etc. And then we come to Modelica. So Hilding and I were discussing a lot, what should we happen with this? And then there was a lucky coincidence. Hilding had an Esprit program in Lund, September 2 to 6, simulation in Europe, and I had COSI, Control of Complex Systems. So I was running another European project, and we coordinated this. And we had a meeting with this in Lund from September 5 to 7. And we invited everybody we knew in Europe who was involved with simulating and modeling. So here's a list of people. I apologize if I forgot some. If I forgot some, you can come and tell me. I will improve the slide. And there was quickly information of the Modelica language group, and the first Modelica specification came out a year later. And then, today you have the 100th design meeting. So I think it's really amazing, what we have done over all these years, because there has been a tremendous development. Here's a list of the original language team, as far as I can tell. And here is the first paper. It was written by Martin Otter, Sven-Erik Mattsson and Hilding, Physical Modeling with Modelica, and it was received in 1997, so roughly a year after the Modelica meeting, and was accepted a little bit later. And then, an advantage by being a professor is that you meet a lot of interesting students. So we had a lot of interesting students doing PhD for this, so here are two of them. Jonas Eborn and Tumme Scheidt. And they did, Jonas did on modeling libraries for thermohydraulic applications. And then a year later, Hubertus Tumme Scheidt did design and implementation of object-oriented modeling libraries using Modelica. And then we had another person who's also well known here named Magnus Gevert. He wrote a dissertation on automotive systems. But a part of this was a friction model. And here's one citation of the friction model. I just picked it up. And this had, last June, it has close to 2,000 citations. So that was an interesting thing that he was involved with. And then we have Johan Åkesson, who should be here today, but he has to do serious model work in the United States, so he's not present. But he was doing a PhD thesis that had to do with the paper industry. And he needed to get inside the code to generate second derivatives for optimization. And that was not easy to get out of Daimler at the time. But Johan had taken computer science from Görel Hedin, who is also here. And he had read about compilers. So I said, Johan, well, you don't need the full Modelica. Why don't you just compile? Use a compiler, and compile what you did. And that was what became the beginning of Modulans, Modelica compiler, when we started to work up there. So there are some interesting students. Now we'll talk about some challenges. First of all, modeling from physics and modeling from data. I think in a certain sense they go hand in hand. But right now there's a lot of hype of deep learning. People believe that by throwing in something to an AI program, you can get out anything you want to. And my own feeling is very strongly that use physics whenever you can, because physics is stable and it's going to sit there for a long time. And then, of course, you have to combine this with measurements and other things. And I don't have time to show you this. Oh. Yeah, so we should use the same. We should also use the same physical model throughout the design process. We should transform the model for different purposes. We should linearize for control design. And here's an area that I think is worth looking into: model reduction. It's very well known for ordinary differential equations. There are some results essentially coming from Virginia Tech in the US for differential algebraic equation. Another thing, I think we should have Modelica online in the loops. And there will be sessions here today about the EFMI, which is a convenient way to... the FMIs are a little bit restricted to now, but an extended version of the FMIs would be very suited to put into the control systems. I need to say a little bit more about physics and deep learning. So that was a slide I had up before. And this I will not be shown, but you should look at when you swing up a pendulum by machine learning. And it takes forever. So look up these slides on the web when you come home. And then you can look at the swing up of a double pendulum with physics-based control, which just swings it up. So then we look at control systems architecture, which I had before. This was the diagram we had with a feed-forward signal generator, the Kalman filter, and the state operator. So for feed-forward, you use inverse model. And I know that Martin Otte has been using this in connection with flight control, and there are other Modelica applications. But that's a nice thing about Modelica. If you have a model, you can just reverse causality, and you can get the inverse model. If you use the observer in the Kalman filter, the nice thing then is by using Modelica in here, you can include nonlinear models. And then when you design the state feedback, you do model predictive control and other things. So I think that DCS vendors, they should provide EFMI's interfaces. I feel very strongly about this. So how do we end this? Well, I go back to my first slide. So here we have control. And we are using mathematics a lot, and we are using physics. And here's the modeling interface, how we are communicating with the physics reality. And I think Modelica is really the right way to do this. And then we have to implement the control system. That's this interface in here. And I think the EFMIs, which you will hear about later on today, is a very nice way to deal with this. And that also captures a bit of the communication. And then, of course, we have to learn the mathematics. So I think what we have to do in here is that we have to educate people who are very good in one of these areas and also know enough about these interfaces here so that they can effectively communicate with other people to do the things. And then I will end with a slide of one of my favorites. Here's a professor in mathematics at the University of Southern California. And then you can wonder, how come that a professor in mathematics writes a paper, Mathematical Models, Uses and Limitations, already in 1968? 1 year after Hilding Modelica. What does he say about modeling? Well, he says like this. Don't apply a model until you understand the simplifying assumption on which it's based and test their applicability, call this validity ranges. And then distinguish at all times between the model and the real world. You will never strike oil by drilling through the map. And then don't expect that by having named a demon, you have destroyed him. When they say, singularity, bad condition, etc. So there are some real problems you cannot divide. And then this is something I like. The purpose of notation terminology should be to enhance insight and facilitate computation, not to impress or confuse the uninitiated. So it's not over yet. So let me just finish by showing you this model, so that we are not alone to think that modeling is important. And here's my final words to the Modelica community. I think we have done a terrific thing. You have brought Modelica to something that is close to becoming an international standard. I think there's more to do, but you have come a good way. And one thing I would like to see is, for example, to develop symbolic tools for model reduction, both by using symbolic and numeric computations. And then I think that you should initiate a discussion to put EFMIs in the distributed control systems. There are many people putting DCS out there, and I think it would not be fantastic hard work to persuade them to put in EFMIs in their system. So if you do this, whatever you have done would be even greater. Thank you very much.